Welcome back. In this last video, I'll work on number 15 and number 16 from my practice problems for exam 2. Now, this is actually my second attempt at this video, although I guess you don't know that, other than I'm admitting it, but I found a mistake in my solution to number 15, so I went back and fixed that first, and now I'm going to go through and explain my solutions to both 15 and 16. I'll leave out the terrible corny jokes that I told in the first attempt of the video, and I'm going to get right into the math. So on number 15, we are working with an application that we often use for derivatives, which is called particle motion. We stole this from physics. And essentially, we work with some functions that tell us the position, the velocity, and the acceleration of a particle as it's moving back and forth on a number line. Okay, not very interesting stuff unless you're into physics, and it leads to obviously a lot of other explanations about how things work in the physical world. Anyway, in terms of derivatives, what we'll do is we'll take this position function that they gave us, and we'll start finding the velocity and the acceleration. So the velocity function here in letter A that we're asked to find, we just use the derivative rules that we've been studying in this unit. So my velocity function is v of t. Please label your answer v of t, and then go ahead and do your derivative rules. So this is going to be 6t squared minus 6t. And I'm trying to make my t's look different than x's or plus signs. So these are all t's with my weird Apple Pencil handwriting. And that's my velocity function. So I'm done with that letter A. No big deal there. In letter B, we're simply going to evaluate that function at t equals 4 seconds. So essentially what that means is plug a 4 into the function you just made. I'm going to make my 4 red here. And the math that we do then is what? This is going to be like 6 times 4 squared, so 6 times 16, minus 6 times 4, which we know is 24. Okay, when you do that math, that ends up being 72. You don't have to label this because in my original question, I did not give any units for my function here. Typically, time is measured in seconds and distance is measured in meters. So this is probably meters per second. It might be feet per second too. But I didn't put labels in my question, so you don't have to put labels in your answer. Just get that 72 down and call it good. Okay. In letter C, we're trying to find intervals where this function, where the particle is moving forward. And in terms of function language, we're trying to find out where the function's increasing. To find out where a function's increasing, we use the derivative. So we're going to use the velocity in letter C to figure out where this thing's increasing, where it's going forward. So what I'm going to do is I'm going to find critical numbers and make a sign diagram on the velocity function. So what we do is we set v of t equal to 0. So I'm just going to write that down to remind you that what I'm doing is 6t squared minus 6t equals 0. This is a quadratic, so you could use the quadratic formula, but it's set up for pretty easy factoring. So I'm going to factor it and just get my two critical numbers that way. When you factor out the GCF of 6t, you end up getting 6t times t minus 1 equals 0. And so there are two solutions to that. Here I get t equals 0 when I set 6t equal to 0. And here I get t equals 1 when I set t minus 1 equal to 0. So these are the critical numbers. Right? Critical points, they lead to critical points, but these are critical numbers. They are places where the derivative, in this case called velocity, is either equal to 0 or undefined. In our case, it's equal to 0. So I'm going to use those to make a sign diagram on the velocity. And all a sign diagram is just a number line, but the only numbers that you put on there are the ones that you found when you found the critical numbers. So this is my sign diagram on v of t. What you do with the sign diagram is you choose a representative number from each of these little intervals, each of the black lines. So I try to pick easy numbers. So like over here, I'm going to choose -1 because between negative infinity and 0, the easiest number I can think of to work with is -1. I don't. And then in between here, unfortunately, the easiest number I can think of is 1/2. Not my favorite because it's a fraction, but we'll deal with it. And then over here, the best number for us to work with is 2. What you do is you plug each of these values into your velocity and see what the sign of the velocity is. So I don't technically need to know the value. I just need to know whether it's positive or negative. But the easiest way to do that is plug it in and figure out what the answer is. So when I plug -1 in, I get 12. That's a positive result. So my particle is going forward when it's over here, but before 0 seconds. Now, having just thought that through, I can't go negative time. So I'm not even going to worry about that interval. Okay. I need to include that in my handwritten solutions. A time starts at 0 and moves forward, so we're not worried about that interval. Let's now plug in 1/2 and see what's happening here. When I do that calculation, I get -1.5. So this thing's moving backward in this interval because that sign on -1.5 is negative. And then if I plug a 2 in, I think I get 12 again. Yeah. And so now I'm going forward over here. Now this one we don't throw out because that's positive time, right? I didn't think this through very clearly when I started. I was just in math mode instead of practical physics mode. So if I'm answering this question, keeping in mind that we're in the real world here, our particle is moving backward on the interval between 0 and 1 seconds. And our particle is moving forward, which is, I think, what this thing asked for, right? It just said, when is it moving forward? So I did a lot of extra work here for, I don't know, because I'm a math nerd, I guess. But the answer for when is it moving forward, it's moving forward on the interval from 1 second to infinity, right? Some people might call that t is greater than 1. And in terms of answering this question, these are the things that we're looking for. So apologies for getting sidetracked there. This is the process, but keep in mind that when you're dealing with particle motion, time starts at 0 and moves forward. It's not the entire number line, so I didn't need that part in the negative world there. Okay, I'm going to keep moving on here because letter D says, what's the acceleration function? So I can get back to regular math here. And for letter D, I just need to do the derivative of my velocity, which is listed up here. So my derivative is going to be 12t minus 6. And then I think the last thing is to plug 4 seconds into the acceleration. So for letter E, my acceleration is, my function's there. I'm going to plug 4 in and do the calculation. 12 times 4 minus 6, which I've already done, and that is 42. Okay, so my acceleration function is 12t minus 6, and the acceleration at 4 seconds is 42. If this did have units, most likely they would be meters per second squared. But since I didn't give you any units, don't bother putting them on there. Now, to finish off number 16 here, I'm going to actually slide this down so that we can see it as we're working, and I don't have to keep going back and forth here. So I'll just put it here, and we'll pick up with number 16. Where's my pen at? Let's get this on here. There it is. Okay, so for number 16, this one is pure math. So I don't have to worry about time or motion or anything like that. I'm just working with this function, which you can see here is a cubic. So I'm going to find out some things about 3x cubed minus 18x squared plus 9. And This is the question that I originally left off the list, so hopefully you've had time to go back and work on it, but I'll run through my solutions here. So we start pretty straightforward. We're just going to find that first derivative. This is the one that tells us where we're increasing and decreasing. So I label this as f prime of x, and I run through my rules. What is this? 9x squared minus 36x. Pretty straightforward. And I'll do letter B here, and then I'll do some highlighting. My second derivative, which tells me about concavity, is going to be 18x minus 36. So we've got the two derivatives down there in the first part of this problem. The rest of this, we're going to answer questions about the shape of this graph. So let me see if I can put this in a position where it's going to be out of your way a little bit here. There it is. Okay, why didn't I do that at the beginning? All right, for letter C, it says use a sign diagram on f prime of x to find the intervals where the function is increasing. For this problem, since there's no context, we're not dealing with physics or time or anything, we need to use the entire number line. All right, so we're going to start out the way we did before. We're going to find critical numbers. To find critical numbers, I'm just going to label this here so you know what we're doing. We take that derivative and set it equal to 0. The first derivative, 9x squared minus 36x equals 0. And as it turns out, this thing does factor like the other one. So I can factor out a 9x, and this will just be x minus 4. The solutions here are x equals 0, and here x equals 4. Remember, this is because we're set equal to 0. You set each term or each factor equal to 0 separately, and you solve to get these. So these are our critical numbers, these guys right here. I use those in my sign diagram. So now I'm going to do the sign diagram. When you're working on your exam, make sure you draw the sign diagram so that I know how you found your intervals. The exam is where you show me that you understand the concepts, not just where you show me the answers. Anybody can get the answers, especially in this day and age. Okay, so I just draw my diagram here with 4 and 0 on it. And this is on f prime, so go ahead and label that so we know which one it is. And my representative values. I'll pick -1 here, I'll pick 1 here, and I'll pick 5 here. Those are the easiest numbers that I can figure, or that I can find in those intervals. Okay, let's calculate the derivative in each of these places. So f prime of -1, I plugged it in already, and that came out to be 45. That's a positive value. It means that my function is increasing. If this were the physics question, it means that it's going forward. But in terms of just a math function, it just means that the function is going up from left to right on the graph, so it's increasing. When I plug in 1, what kind of an answer I get here? I get -27. That's negative. That one is decreasing, so that function's actually moving down if you were looking at the graph. And then over here, f prime of 5, that's 45 again. So again, that's positive, it's moving up. So we call this a sign diagram because it helps us see the sign of SIGN, the positive or negativeness, if you will, of the first derivative. But it's given me my intervals that I need to answer the question, not only where is it increasing, but also where is it decreasing. So my answer for letter C is just going to be the increasing part. And so I say f of x is increasing on, and then what I'll do is just union these two intervals. So it's going to be this one and this one. So that would be -infinity up to 0, and then typically we'll stick that together with a union symbol, and then that goes from 4 to infinity, that other piece. So that's my answer to letter C, and then letter D just says, hey, what about decreasing? So I'll just stick that, I'll just stick that right here, and I'll say f of x is decreasing. And it's decreasing here in the middle on 0, 4. So between 0 and 4, that thing's decreasing. Now, you can look at the graph of this function just to verify that you did it right with Desmos, and you'll see that it sort of has this shape, that it goes up. Let me do this in light green or something, because I'm going to mess my picture up. It goes up between negative infinity and 0, and then it goes down between 0 and 4, then it goes back up again. That's a typical shape of a cubic. So that's kind of what we're showing there. Again, if you plug the original function into Desmos, it'll have that shape. Okay. And then now letter E, I'm going to slide over here so I can keep this on the screen. Letter E is asking about the sign diagram for the second derivative. So I'll do letter E right here. My second derivative is 18x minus 36. So I'm going to look for candidates for inflection. So these are kind of like critical numbers. But when you do it on the second derivative, they're candidates for inflection instead of critical points. And the way we'll do this is just set 18x minus 36 equal to 0. When you solve this equation, you add 36 divided by 18, and you get x equals 2. So this is my candidate for inflection. My sign diagram will just have 2 on it. I don't know what I'm doing with my colors here. Sorry about that. My sign diagram, this is on f double prime, and the second derivative just has a 2 in there. And again, I'm going to pick some easy numbers. So over here, the easiest one I can think of is 0. I love doing math with 0. And then the best we can do over here is 3. And what we'll do is we'll figure out the second derivative of 0. And when I plug 0 into 18x minus 36, I get negative 36. Because that answer is negative, everything over here is concave down, which you can kind of see in my green, right? In my green over here, it was concave down. So that's good. And on this side, when I plug 3 into my second derivative, it comes out to 18. And 18 is positive, so the shape of the graph over here is concave up. And you can kind of see that where I drew the green, right? It's kind of smiling over here. So that's good news. Okay, so how do we answer the questions? For letter E, we want to know where the function's concave up. So I will say f of x is concave up. I got to spell it right. From negative infinity to 2. And then for letter F, f of x is concave down. 2 to infinity. I'll stick that here because I'm kind of running into my letter D there. And then we do have a letter G here. And the letter G is saying, hey, do we have any inflection points? And the way you check for inflection points is you look at your candidates. And if the concavity switched from down to up or up to down, if the concavity changed, then that is an inflection point. And in our case, it did change it too. Over here, it was down, and over here, it was up. And so we'll say that our inflection point occurs at x equals 2. You don't need to give me the y coordinate here. I'll just say inflection point at x equals 2. Okay, so you don't have to give, just give the x coordinate. That's fine on that one. We need an interval here and an interval here, though, and we have that. Okay, so both of these both of these exam questions deal with the first and second derivatives, and they're interpreting the results of the derivatives. So the first derivative always can tell us where our function is increasing and decreasing. And the best way to do that is with a sign diagram. The second derivative can tell us where our function is concave up and concave down. And again, if you make a sign diagram, it's easy to find those intervals. I just want to quickly go back and talk about my mistake that I made in number 15. And I'll fix this on the written results or solutions as well. I actually didn't make any mistakes. I made a bad interpretation. Because this problem has context, and the context is that we're checking a particle's motion after time zero, right? Because this function has context, we have to make sure our answers represent that context. So in the case of letter C, we're only worried about positive time intervals. So from 0 to 1, this thing happens to be going backward, which is not what they asked for. And then from 1 on, anything greater than 1, this thing's going forward. And so just remember that I made that little mistake there. You don't have to worry about negative time when you work on number 15. Okay, that video was very long for 2 questions, but hopefully it helped you see if either you're on the right track or where you made some mistakes. If you do get questions because you've watched this, please let me know. I'm happy to answer them. Ask the questions before you take the exam, not after. Ask your questions before. In the meantime, take care.